we are going to start with this seminar. We have here essentially people from the University of Granada. We also have some invited people in the Google Meet, and we also are also recording the session. So we are going to have a research seminar here for presentations. I'm going to start with a small presentation of the research group here in Granada, and we have the opportunity of having here researchers related with antenna topics, so all of them. We take advantage of their presence yesterday in the thesis committee of Cleofás Segura, and today we are having this presentation. So I'm going to be the beginner with the first presentation. It's an overview of the research capacities and the research activities of the SWAT group here in Granada. And then we will have the rest of the presentation. Initially the presentation, and then a discussion or questions period. So everything is ready. I'm going to start. I'm going to check if everything is going properly for the recording and the online session, and I'm going to do the presentation. So. Well. So, as I have mentioned, the idea of this presentation is not only to have an overview of the group, but you three, in order to have an idea of what exactly we are doing, what are our research lines, what are our interests for future. Also, if you see some kind of possible collaboration or whatever. So, as a group, we are here in the University of Granada, particularly in the School of Computer Science and Telecommunications. Is the campus in which we are right now, and also in the research center that is the CITIC center, that is the research center associated to the engineering school here. In fact, it's the building in which we are. Here we have also some facilities, not only the research part in the building, but also the labs of the group, as I will present later on. As an outline for the group, we are a recent group. It was founded in 2018, or sorry, 2015. We are two full professors, one associate professor, 4 senior researchers, 4 PhD students, if I'm not wrong. One lab technician, more than 6 master thesis students, and more than 10 bachelor thesis students. And this is dynamically changing during the year. So perhaps these numbers are almost exact, but not exact right now. As I mentioned, the group is quite recent. We have 8 to 9 years of expertise just as a group, as a radio frequency group here in Granada. It is true that former members and the initial members of the group were in other research groups of Spain, coming from other universities. But now the group here is a consolidated group. As the main research line that we may have in the group, they come mostly from the interest of the people that conform the group, but also from the people that have joined the group during the time. So first of all, manufacturing of microwave and millimeter devices is our core topic. Our research line, main research line, is the things in which Juanfra and me, the leaders of the group, start working with the PhD thesis and with our initial research. But also we have a research line related to characterization, a singular lab that I will present later on, for millimeter and microwave devices, and everything related to the characterization of the device, S parameters, acquisition of radiation pattern, but also in the recent times, radar clock session and so on. Additionally, we have a line related to propagation channel characterization, emulation, modeling, and everything related to propagation channel, but also in going in frequency as high as possible in terms of the frequency we can measure and we can deal with in the research we do. As a as a concept, as a leitmotif in the group, we try to go as far as possible in frequency, millimeter waves, but not only millimeter waves, and all the things that we try to do in long term are related to go further in frequency. As you may see, the facilities that we have reach 300 gigahertz in measurement capabilities. And also, as I have mentioned, well, this is duplicated, sorry. And also a line regarding optimization. We also collaborate with Francisco Luna, is a professor in University of Malaga. This is a transversal collaboration because optimization can be applied almost for everything. But here it is useful to have not only optimization in the designs that we do, but also to be effective in the development that we do, and also to have an idea of why something is working in such a line. And perhaps optimization sometimes, depending on how you do that, can give you the information about how are you dealing, how are your simulations evolving, and finally how you reach a particular path. As collaborators, we have, considering universities, we have collaborated in time and still collaborate. It's a very dynamic collaboration and very fruitful with Universidad Politécnica de Madrid. Is my former university, University of Málaga, Universidad Pública de Navarra, Universidad de Extremadura, Universidad de Vigo, Universidad de Sevilla, Universidad Politécnica de Cartagena, and most recently, Universidad Autónoma de Madrid. Also, as international collaboration, we have collaboration with ADH, with Sorbonne University, with Aalborg University, with Instituto Universitario de Lisboa, Alto Ioquisto, University of Alto, and EPFL also in Switzerland, among others. These are the main collaborations. Also collaboration with companies and contracts with Ericsson, Viatec, Valeo, Sener, Indra, Airbus, EC, Senset, and many others companies. Most in the recent years, more active in this part of collaboration with companies in the last years. As technologies that we have, as I have mentioned, we have this main line of designing the radio frequency devices. This is inherited of the experience and expertise that we have as a group. We have all kinds of developments in conventional waveguide technology, but also gap waveguide and their different versions of gap waveguide needed as we go further in frequency, and the gaps and the leakage of field is an issue of great importance. Also printed circuits and everything related to 2D technologies, reply microstrip, but also SIW technology and the different versions of this technology, LTCC and so. Then multi-layers, also multi-layer structure, just considering the architecture that we select for the designs. Also devices related to lenses, that may be considered as the conventional dielectric lens with a uniform permittivity or with a variation of permittivity in the lens and the structure fixed. This is of great importance recently with the evolution of printing technology and 3D printing. But also we have been dealing with what we call metallic lenses. These are not metallic lenses, but are devices that conform and confine the field because of metallic structures inside, that in a particular way you can define or tune the field evolution, the field guidance through the structure, so that finally you get the same effect as if you were dealing with a lens. Has some restriction, you can have it in one plane but not in the other, and we will see. Also, lens surfaces working as lenses or just focusing structures. And we have been dealing also with array structures and all the designs regarding array things, such as phase arrays, transient arrays, reflect arrays, and so on. Finally, also a line related to metamaterial, metasurfaces, FSS structures, and more recently structure in time and space varying structure. So as continue with the with the outline and with the main with a wide vision of the group. We have our facilities. We have an anechoic chamber from 10 gigahertz to 330 gigahertz. As I mentioned before, our main aim is to reach frequencies that are not typical ones, and where the facilities are not reaching such frequencies. We have a planar cylindrical and spherical acquisition system. It's a smart design that doesn't need rotatory joints that are the main limitation when you go further in frequency. And well, all the devices were related to this chamber. This was the initial facility and the main facility that we have. It was mounted and finished in 2018. As I mentioned, this is the origin of the Singular Lab. Now the lab has many other facilities I will present, and this is considered right now a Singular Lab by University of Granada. This is a quality level given by our university, but as a recognition of having singular installations not only in the University of Granada, but in the case of the national and international sphere. I mean, if you have a look to our facilities in the anechoic chamber, we received the visit of some companies, some really top companies, just measuring prototypes in millimeter waves for 5G, and they are with commercial equipment, and they measure it here. Also, we have an additional facilities. This is a compact range, multi-source compact range that is mobile. You can move it, but it's huge. I mean, you can move, but it's like moving a car, just pushing the car. And you have here a multi-source scenario that you can illuminate your device under test with different planar waves coming from different terminals or different. You can emulate a communication system inside, or you can just measure and analytically measure the parameters, the radiation pattern of the structure. It's quite versatile and useful, but it's still under mounting. We are this month and the next, Jan and July, finishing some of the facilities of the group, thanks to an international infrastructure project of the national government, well, with the next generation funding from European Union. Also, we have an anechoic chamber just for electromagnetic compatibility directly. We don't do certification, but we do pre-certification. We are not interested in having all the resources and all the necessities for certification. This is quite demanding. But for pre-certification is quite useful, so that companies come here, see if they are fulfilling or not the requirements, and finally, when they see everything is working, they finally go to a certification place in order to get the certificate. Also, we have a monostatic, bistatic radar cross-section system under construction. Right now, the chamber was also begun to do this kind of measurement, but was like a homemade design, and also in a small chamber, so limitation in terms of the size of the things that you can measure. But more recently, we are mounting here. You have a photo of the system in a current moment. It's a yesterday photograph, and if you see that the absorber are not already placed and the system is not mounted, but you may see that you have the bistatic system. There are two arcs for systems, so that you can measure and receive for the same receiver that is monostatic, or you can have bistatic for 4 different sources. And also in the complete system, there will be here a reflector for a compact range, so that you can illuminate and generate a quiet zone also for the measurement of a structure, or more critical structure, or a structure that cannot be translated from near field to far field. So, but this is something that is going on right now, and also with research underneath. As you see, to have this system fully working and fully tested will be a challenge in the next months. Also, we have facilities related to characterization of materials, mainly related to free space acquisition transmission, reception, and everything in between. We have a quasi-optical table, a quasi-optical bench that can have accurate measurements of materials in two ways. We have this line of characterization of materials. First of all, characterization of classical material or new materials in terms of permittivity, permeability, or so, but also the characterization of materials that may have any kind of change because of the polarization they receive. You can polarize or just with DC or whatever, but you can change any of the properties of the physical properties of the material so that you can change something. Something is, for instance, conductivity or permittivity, or just tuning this material so that you can have any kind of reply that is different. This is useful, for instance, for low observability. If you get a material that is transparent, but if you polarize it, it becomes not reflective, perhaps not having a good conductivity, but absorption, bad conductivity, but absorption. This is useful as for instance, in an aircraft, in order to get invisible to a radar system. So this kind of new materials, new paintings, new substrates should be tested, and should be tested also for high frequency. Again, we go further in frequency to the 330 gigahertz as you see here. Also, some manufacturing facilities. Not many. We have some 3D printers, conventional printers, also fast PCB prototyping, also a metallic printer or pseudo-metallic printer, dielectric with metal 3D printer recently acquired. And the idea with this is to have the possibility of having fast prototype, initial prototypes in order to make a proof of concept. Mainly, if it is needed, we go externally to get our prototypes in research. But if we can, we are really proud, and we like a lot to have prototypes, and also to confront limitations and problems regarding the manufacturing of what you are designing. So as a group, something that we love is to control all the process, and to present something finished and something closed. So you start with the idea, and with a paper and a pen, with the idea and the outline of your idea. Then you go through the analytical or the simulation steps. Then you make your prototype. You try to make it here homemade, and then externally in a better way. And finally, we measure it in our facilities, so that we control all the process. And also, it is not to produce science. It is also to form people. So the thing here is that controlling all the process, we can form the next generation of engineers, of researchers, in a smooth way, in order to gain all the concepts that you need. Something typical that may occur is that you have people that are really good designers, but they have not confronted problems in manufacturing. So finally, they do devices that are of paramount importance, but finally, when they go to manufacturing, there are issues that are quite easy. If you know something about manufacturing, from the very beginning, you identify that you cannot do some techniques. And this is an information, an experience that you get in time when you are a researcher. Here we have people with a lot of experience. I'm thinking about José Luis Masa, that has huge experience, for instance, regarding whatever related to additive manufacturing or diffusion bonding or whatever, and a lot of essay and error. So this experience in the next step of manufacturing is of paramount importance to get knowledge of what you should have in the simulation steps. So this is why we like to control everything. And also because I like the students that are with us to be to feel that they have learned something specific that is useful if they want to go to industry and to apply their knowledge. And for instance, the design of radio frequency devices in industry is something well established and needed, and also our people is well formed to afford this afterwards. So I'm going to present as an outline, as a wide view, different prototypes and different systems that we have elaborated. I'm going to be more or less not fast, but like just presenting it. And if you have any question about or any curiosity, you can ask. So first of all, radio frequency devices. If we divide the the terminals in terms or the devices in terms of what is the radiation terminal, the antenna, or whatever is previous to the antenna. First, we have the radio frequency devices, for instance, phase shifter. These phase shifters are of paramount importance when you are configuring any radio frequency system that should change dynamically or that should be reconfigurable. So we have been working in different technologies in having phase shifters, fixed phase shifters, tunable phase shifter, mechanically tunable phase shifter, or electronically tunable phase shifter. For instance, here you have a phase shifter with controlling with varactor for controlling, fixed phase shifter in glide technology, also glide and hold based technology. Also, in order to get a phase shifter that has good properties not only in the phase that you can acquire, but in the linearity that you may have, or in all the desired bandwidth that you are considering. Also, mechanically tunable phase shifters. We like a lot to have funny ideas and just to develop them. And every time I receive a student, a PhD student, or whatever researcher here, even if they are young with an idea, we tend to say to them, okay, propose things and we will discuss in order to get smart ideas that could be useful. We have our mind is my mind as a researcher is focused in one particular line. So perhaps I'm losing options because I don't see them. So sometimes the diversity that the people introduce is quite useful in terms of perhaps not having a close idea, but perhaps introducing some point that gives you the idea finally, and you can get the new results. This was, for instance, this prototype is quite it's a stupid prototype. I mean, it was a work that we decided in an afternoon with a coffee, and we thought, okay, we can make mechanically something that closing the waveguide. We have, okay, the problem here are the resonances, but if you introduce some slot and some periodicity, you can close, so you can have a stop band in the for the resonances in the structure, and you increase linearity. So finally, you get smart prototypes from simple ideas. Also, as feeding networks, a lot of elements such as mathematics in different technologies. I will present here some examples. For instance, substrate integrated waveguide elements. This was one of the elements that was in the thesis defense yesterday. Also, Coupler or filtering structures. Also, considering that maybe leakage is always our enemy, but not always. It's almost always our enemy. But if you consider that you need some coupling elements, or you need some filtering structure, but in an easy way, this leakage can be useful. As you see here in this structure, this is a structure that blocks leakage here and there, but permits, depending on the structure that you put, permits the leakage of the field from the coupling from one line to another line, but in a particular way. And you can make smart things. Even you can take concept from optics or from photonics, for instance, the classical Fabry-Perot, but just dealing with that, because we are in the frontier of considering things that are radio frequency but are entering in optics. And you can take the concept of optics. Later on we will see, for instance, the idea of lenses. So that you can take a lot of consolidated ideas from optics here that are innovative. Also, active elements. We are, as you may know as researchers, there is one non-close problem that we have had during the last 20 years, but I mean 50 years, that is how to get reconfigurable elements and reconfigurable devices in radio frequency and increasing frequency. And this is not a closed solution. In fact, everyone is proposing, everyone is putting the name of reconfigurable in their devices in order, because it is commercial. I mean, you can go with a paper for a journal saying that, and this reconfigurable idea is the one of the main purposes in the recent year. But one time and another, we have a lot of problems in getting real solutions, valid solutions, and with proper behavior or proper performance. And as an example, I normally say, when I was in my thesis 20 years ago, we were trying to do some reconfigurable elements, and we explored the use of MEMS with these devices. Well, after 20 years, it is more or less the same. I mean, if I start my thesis again, I will explore more or less the same that I explored 20 years ago, and the technology is not mature. For instance, MEMS were thought to be the future, and now they are a possibility, but they have a lot of problems in terms of reliability, repetition, and they break easily. So finally, they are not the solution. So we have not found a really good, really close solution. So here we have explored some graphene-based elements. This is quite interesting because perhaps not in the millimeter wave band is useful, the graphene, because it has a lot of absorption, not good conductivity. But if you go further to sub-terahertz or terahertz, the graphene start to work properly. So it's like having a metallic sheet or not, and the property is if your system needs something that is like a door open and closing, the graphene could be an option. Some ideas, introducing this into elements, into cells, also devices, but electronically variable devices, but in the active element itself, in the radiation element itself, not in a previous structure. Also varactors over structures here, some designs, and also reconfigurable FSS structure. The main thing here, as you may know, is that if you use technologies such as varactor or pin diodes or so, you have the problem of parasitics, but also the problem of feeding the device and the position and the physical place of the device and the space that they occupy, and also the problems that it generates in terms that you cannot have a sandwich, for instance, with a pin diode inside because it will bend. So this is difficult in terms of getting the device working, but also getting all the surrounding things that is needed to polarize these devices. Also, as designed Broadband waveguide designs, also helix antenna designs. This is, for instance, this is in collaboration with UPM years ago. We have a lot of, as I have mentioned, a lot of collaboration with universities. It also comes from our history. I come from the Universidad Politécnica de Madrid, and it's the place I carried out my PhD thesis. So I have tried to get all this knowledge and to take it here. We are as groups with the one of Madrid. We are like siblings, and we collaborate and we like it a lot. Also, structures in array technology with planar or stacked circuits. Also, some smart devices. This one of my thesis, but I'm very proud of that because changing here the position. This is not 2D. This is you have this multi-layer, but here you have a layer that is orthogonal, and was really easy to do that well with a good performance, and this gives a lot of facility and a lot of possibilities in order to get a device with a phase shift, for instance, inside. A lot of devices considered in terms of array technology. Well, we have here the reference of some of the papers. But also array antennas in terms of additive manufacturing, 3D. These are our first explorations of devices in that way. This is the thesis of Ángel Palomares that nowadays is associated here. Also antennas with, for instance, radial slot array. This is also a collaboration with UPM. Arrays in subset integrated wave technology, and also things surrounding the production of devices. If you go to array structures, you need to define which is your array, which is your array distribution and configuration in terms of phase, in terms of amplitude. And first of all, you can have something fixed or something well established in terms of well thought in order to get a particular pattern or particular thing. And this implies also to develop some processing, some formal processing in order to get the proper pattern, the proper image of the faces of the cells that you need to conform the array, and so. And also you can get some optimization processes in order to get almost a real-time solution. Because if you think in reconfigurable elements, you may think that you can have this possibility of reconfiguring and going almost in real time reconfiguring, but you also need the information of reconfiguring. You need the information of which phase add to each element, and this should be also in real time. It's something that we have not to forget. The elements that we need previously in order to get our functional, our system as a whole. So some patterns here, as you see, with depending on the configuration, you get the desired pattern or not. Some experiences that we have had in reconfigurable intelligent surfaces. Here you have some structures. Also, what you can consider RIS structure, but also like a smart reflector eye, but also a structure that is making things like polarization or change of rotation of the polarization or whatever. So many structures that can be in this array structure-like design, but with many possibilities in terms of the final performance of the structure. Particularly considering transmitter arrays and reflector array, here you have some examples and elements developed in the group, electronically reconfigurable or passive configuration with wideband, multi-frequency, and so on. And here we reach also our experience in RIS technology. This award developed mainly in one PhD thesis, the thesis of Marcos Baena. And here we have developed some RIS structure. First of all, fixed structure, then reconfigurable structure in terms of having mechanical movement. We have explored micromotors, also exploring magnets, electromagnetic magnets that have commutation between the two positions. And also, well, if you see here, you have like elements that are going up and down so that you get your zero or half wavelength behavior. And also the mounting of that in the laboratory and the experience in that. I should say that for RIS structure, it's not only the design and to manufacture it, is to characterize it. This is a lot of time and a lot of effort to be put. If you have a RIS structure in one wall, you may think that this is like replicating the path, but there are problems such as the size of your device, which is the amount of power that you take and you replicate. So you have to characterize it properly and to see if your device that is working finally works in the scenario, the environment that you have. More things related to that, and idea is to add, for instance, the electronic devices. We are working in this also in the thesis of Marco, but also in the work of Angel, and also is the reconfigurable line is one of the flagship of the group right now. And we have also experiments or initial things related to 3D structure, even 4D structure, considering time as another dimension. Lenses, as you may see here, Fresnel lenses, conformal lenses with a particular pattern, depending on the particular performance that we need, we define it. But also the concept of metallic lenses that I mentioned before is like, use your device, tune inside your device what you are doing, move things, confine the field, change the wavefront, and you finally get the behavior that you want. Here you have an example, for instance, of a horn structure that is like having a lens structure inside. So these holes change the propagation constant in each point to the other, so that you equilibrate the phase response and you make an homogeneous phase response and change the phase error, the classical phase errors of a horn antenna, so that you get a pattern that is more directive and also with a compact design. You don't need a lens afterwards. You have the lens inside, and even in that case, if you go to the optimum design for a horn, this is big. But if you replace the optimal design with this kind of design, perhaps you have the same performance, but 1/3 the size of the optimal design. Many devices, as I mentioned before, we love to manufacture everything, and we love to measure everything. And more structures in this, like for instance, for a 4x4 array of elements in substrate integrated web technology. Also more prototypes. The second one is of the thesis yesterday, but also things related to the application of our antennas into system. For instance, also experience in harvesting, in energy harvesting, It was made by Antonio Alex a time ago. And not only with the system itself, and considering the circuit and the problems that the parasitics and the things that consume power and doesn't contribute to the system should be taken into account and characterized, but also the antennas, ultra-wideband antennas or antennas that are really good for particular bands, for instance, Wi-Fi or 5G or whatever. Then the last line is the propagation channel line. And we have a lot of experience. This comes from the experience that Juan Valenzuela, my colleague, has among the years and along the time. And this line is really fruitful in terms of considering what is happening for higher frequency. There are many things that are well established and well known for microwaves that are not known for millimeter waves and perhaps working in a completely different way for millimeters. For instance, you may have a system that is quite good or quite bad for millimeters inside in an indoor scenario, but for instance, in millimeters, you become to an option that you say, okay, the limitations in microwave here because of the wavelength, because of the nature of the problem, and so you get that field is enhanced instead of being reduced. So you find funny things or interesting things that are really useful. This line was continued here with the work in the thesis of Alejandro Ramírez, and we also collaborate with him. He's a postdoc in Aalborg University right now, and also with the thesis right now of Juan Galeote. Here you have indoor channel characterization up to 330 gigahertz. Since we can measure till 330 gigahertz, we measure everything till this frequency. And we make small things in order to get the cables able to reach and to have a dynamic range in that. Also, as you may see, propagation channel plus the read systems is that, okay, if we have a lot of elements in terms of devices that can be working, why don't we use and we do a scenario in order to decide everything related to that. So here you have some tips about the working of a system in millimeter waves when you use some replication with reads in a wall or whatever. And also some experiments related to diffuse scattering. This is a collaboration also with the Politécnica de Cartagena. Also, Esta is related to a human blockage with a system. Perhaps this in microwave frequencies, this is basic, but in millimeter, this is not no more basic thing. It's a quite important thing. Things are more directive. You may have radio frequency links, and if you go through, perhaps you are falling down the radio link inside the building. So it is something to take into account. And this is the overview I wanted to present to you about the group. As you see, we have a lot of things in time. We have been working since 20 years ago. So we have a lot of things developed. But also, the idea that I want to transmit to you is that we love making funny things and smart things and new ideas, and to be with a smile doing that. So this is the aim, or this is the philosophy of our group. It's the idea that I would like to transmit to you when presenting the things that we have in the group. And this is everything from my side. If you have any kind of question or whatever.
Thank you very much.
Yeah. I have no doubt.
The four sources chamber that you have presented, what is the merit figure that you measure there? I mean, you are illuminating with the four sources?
Yeah, you may have the idea of, okay, if you think about classical antenna measurement, perhaps you only need one source, just one source. And you measure, you generate your PSO, you receive, and you evaluate. But imagine that you want to evaluate the performance in terms of throughput of your mobile phone. You can place the mobile phone inside. You can get, for instance, you can replicate the base station behavior. For instance, 3 different base stations coming from different distances. You can configure that in the chamber with the different sources with a planar illumination. It's like having far away your radio station. And imagine that you are, for instance, feeding your terminal with 3 different structures. You may evaluate, for instance, the hard handover or the soft handover. You may configure 2 of them with soft handover, is only terminals but the same core network, and the other one terminal but changing also the core network. And you may say the 3 scenarios: hard handover, soft handover, timing handover, changing the power that you receive. For instance, you may alternate one of them, and it's the same of having far away or closer the base
because
station.
it's not defined the kind of test that you are going to do. It's so open. You can measure whatever you want or wherever you imagine. For example,
this is the point.
The carrier versus interference, whatever.
Yeah.
It's not as such canonical as an echo chamber that you measure the radiation pattern, gain and no more. But here, I was thinking, which are the typical tests that are established there?
Yeah.
Because
this is why
I imagine so many things that.
This is why I put this example for instance. It's like we as classical radio frequency engineers, we think that the world ends with the radiation pattern and with the. And it's not our problem how the antenna copes with the system or how the system works. But right now, if you go to industry, they most of the time don't want to know the particular radiation pattern, but they want to say to you, okay, if I put my antenna here, I'm receiving what is the performance as a whole. And more and more in time, this kind of performance is more needed or necessity for the industry. So this gives you versatility.
Yeah, that's right. But I mean, you are open to the company. What is the many figure that they want to define?
For instance, you can evaluate the latency that you have. The different elements that you have in the definition of 5G or 6G, for instance, and limitation regarding latency, throughput, you can evaluate. For instance, you can evaluate the evolution of your throughput, just changing attenuation in the illumination that you have. You are is equivalent to be linearly retiring, being farther with your antenna, but perhaps the performance in terms of throughput is not linear. It's changing exponentially or whatever, or one threshold, and everything related to that has to be evaluated. And this is the point of having this kind of devices. Also, it's such versatile that you can open the door and use also the outside the scenario as another field.
Yep.
So you can have indoor, outdoor, and
semi-indoor.
Yeah, you can configure, or finally just use it.
Wherever your imagination can give you.
Yeah. Or finally just as a fridge, to put something inside.
Okay, thank you.
I was interested. You show some prototypes.
Yeah. We can go to
different, because you have different approaches.
Yeah, for instance, here to prototypes
done by yourself.
Yeah, this is are done here and are done with the formula printer. If you need more, well, the accuracy of these printers are okay, but you have some second line problems that you may not recognize. In the micro scale, they are good enough. You have microns of resolution, but in the macro scale, you may have problems. For instance, something that has to be rigid and completely plain, and you see that it's not plain, it's little bit banded, a little bit bended in some way. And so you have to think about, okay, go to your design. Since we have, for instance, we have seen how bent the structure is when we do with size, with dimension. So when we do the design, we consider this bend in the design so that we have an additional phase correction in order to eliminate that. So this is also why I told that it's important to have manufacturing in your head when you are doing the previous step.
Which is the frequency here?
I think, Angel, this is 70 or 60 gigahertz. This one?
60. And did you assess the role of losses? Because it's dielectric, right?
Yeah.
To understand this material.
Yeah. Well, this is dielectric, but since you have your material or not your material, for instance, here the reduction is to eliminate material, so the losses are not so high. But I recognize that one of the problems is the dielectric losses.
With that printer.
Yeah.
Well, this is a new printer that now we have similar to that.
And so because I expect that you with the realized gain you will lose at least
3 dB you are going to lose. Yeah.
Because if you go for space, they will kill you.
Yeah. But if you go for a space, they are going to say, okay, your technology is magnificent, but then you're using technology of the 50s.
Yes.
Because it is so expensive to send something.
Yeah.
So give me a reflector, or give me a box and a cat inside, and then send the cat. So, but I prefer to do things that I have been doing 100 years.
Many years ago, reflector rays, for example, were impossible to be in space on board.
Yeah,
because
now they are.
Now they are.
They are, but very limited.
Yeah, they try. This sticker is pushing a lot.
Yeah.
And this one was done with which machine?
With the Formlabs.
Formlabs, which is a tool.
No, it's quite. It's
2,000, 3,000 euros.
Yeah,
it's a car.
But
more than a Ferrari.
More than a Ferrari, no.
It's really cheap. Considering what you get, it's really cheap. Because if you want to go a step further in terms of accuracy, you put 2 zeros in the.
Because I'm interested because I'm doing marketing and scouting the market. Yeah. And I see that they can ask even what we do.
Yeah, perhaps Formlabs right now is not the best option nowadays. In terms of price, it's really competitive. But perhaps you have more options right now. But 5 years ago or 6 years ago, we had a hit in 7 years ago or so. Was the only one in the market that was doing this kind of, it was like a revolution. To get in your laboratory microns of resolution.
The reason why they are so expensive, it's not because they are expensive, it's because they have to recover the investment.
Yeah. But even in that case,
there is less
they are not expensive. I mean, I can buy a machine like that for 3,000 euros. 3,000 euros compared to a
the performance are not the same.
Well, but also the performance is okay. You may see our printers there. In fact, we had money and we bought 2 at the same time, so that we can print simultaneously different structures.
Yeah, maybe at this frequency is roughness.
Yeah, but also roughness in terms of the dielectric here is not demanding. Would be demanding if you want to metallize, for instance, this structure and finally.
That's also my question.
Yeah. In fact, well, since we are always trying things.
My question for the future is: do we need?
We are no chemist people, but we try. So, in fact, I know that Ben has a lot of experience just putting things and mix it with that and I like your panel.
There is maybe that is doing wonderful prototypes in stuff. They are very expensive machine, but in the end, sometimes or often you can just use coating.
Yeah.
It's much cheaper.
Well, finally, if you need, you can also go to site and you get, for instance, Jet Metal in France. They metallize things quite.
I'm gonna present you all the options next because I'm gonna speak about all these kind of technologies and we can talk about later.
I love the work of José Luis because it's like in my mind, but in 3 years or 4. So
it started a little bit before.
Yeah. I will show you all the possibilities. If you want to write something or to think about, we can talk about that.
Yeah, I've done some market scouting.
Yeah, no.
There is a huge possibility. Then there is the Chinese tools that probably they are much cheaper.